We're starting this unit with review, looking at parent functions, transformations, and also using word problems and different types of equations to model word problems. So first off, we're going to go through the different parent functions we've learned before. And remember, a parent function is the simplest function of a specific type that gives us a specific shape. So the simplest line is y equals x. The simplest quadratic is x squared. The simplest cubic is x cubed. And see if you can fill in the rest of them, but I'm going to write the equations first and then draw the graphs. So we have the square root and cube root. We have absolute value. The exponential and logarithmic are a little different because we have a general form, and then we have lots of different ways we can write that because we are going to plug in something for b. So the general form of a parent exponential function is just some base to the x. We have a couple rules. That base has to be a number greater than 0, and it can't be a 1, or we wouldn't get the right shape. We just get a straight horizontal line. So some examples of that would be 3 to the x, e to the x, 2 to the x, 10 to the x. Any of these are examples of parent exponential functions. Logarithmic functions, our general form is also similar. We know logs and exponents are inverses of each other. So examples here are just picking different numbers for bases. So I could use a 2, and I'm going to write our two special ones. I could use an e for my base, which we actually call ln of x. If I choose a base 10, we don't have to, that's wrong, we do not have to write a base. We just write log of x. So ln of x means we have log base e of x. Just log of x means we have log base 10 of x. So going back through these, each of these shapes tells us something about the operation. So the linear parent function just says that whatever I input is also going to be my output. So we end up with a straight line with a slope of 1 that goes through the origin. A quadratic graph, x squared, we end up with a parabola. And this tells me something about squaring numbers. We can tell they're always positive because my range is positive numbers are 0. I can tell they grow faster than just taking a number, right, because we have that bend up in the graph. My cubic parent function, we know another name for this is the disco function. And this tells me that when I cube numbers, if I cube negative numbers, I get negative answers. When I cube positive numbers, I get positive answers. We have a similar bend, a little bit more of a bend than x squared, but we have a similar shape. My square root parent function is my first one that has a restricted domain, which means I can't use any number I want to plug in. So when I look at this one, first off, it tells me I can't take the square root of negative numbers and get a real answer. And it tells me that I need bigger and bigger numbers to get the next integer as my answer. I have to go all the way from 9 to 16 to get an answer of 3, square root of 9, or 4, square root of 16. Cube root is similar, but we are going to see that we can take the cube root of negative numbers. So we do have negative values for the domain. An absolute value graph shows me that absolute value always makes answers positive. So my range values are only positive numbers. I'm not doing anything else special, so I have straight lines. Moving down to my exponential and my logarithmic graph. My exponential graph shows me, first off, that anything to the 0 is 1. It shows me that as I raise things to exponents, they grow quicker and quicker. But if I use a negative exponent, I get a tiny fraction, not something that would go below 0, but we have that other side that gets smaller. And the logarithmic graph is the inverse of the exponential, so it will be a reflection of y equals x. The log of 1 is 0. What exponent for any base gives you 1, right? That's 0. And it grows slower, so it's kind of similar to a square root graph, except this one we have a tail, we can't take logs of negatives, and so on. So as I drew these, I kind of talked about these types of functions and why they look like they do. And they're a basis for really any type of graph we do. So with these graphs, to move them around to where we want them for a word problem or just for really anything we're doing, we use transformations. So the first one, and we've focused on the first 8, we introduced the last one before. I'm going to change it up just a little bit. If you're watching this video in 2026, it'll be a little different every other year. It should be consistent with what we did in Unit 6. A reflection in the y-axis first, though, we make the x negative. A reflection in the x-axis, we make the function or the y negative. When I shift left A and right A, that's where it works backwards. So I would assume left was negative, if I hadn't learned this before, but I know it's positive, and right is negative. When I go up and down, I put that change after my function. I'm adding or subtracting from the y, not from the x. Vertical stretches, I have this line down the middle, because a vertical stretch and compression have the same rule. We put a number in the front, and if that number is greater than 1, we have a stretch. And if that number is between 0 and 1, we have a compression. So if I put a 1/2 in the front, I would compress. If I put a 3 in the front, I would stretch. My horizontal compressions, instead of putting the a value in the front or times the whole function, I put it in with the x. So these two both have the same rule, and we're going to have similar conditions. Now really, and I'm going to write an example here, if I have something like f of 3x, just like my left and right, these work backwards from what I would think. So it looks like that should be a horizontal stretch of 3, or stretching out 3 in the x times 3 in the x direction, but it's actually backwards. So it's a horizontal compression of 1/3, or 1 over that a value. So if I want to compress, I actually need to use a number bigger than 1. And if I want to stretch, and we'll look at an example in a second, I need to use a number between 0 and 1. So for example, if I want to stretch, and I did 1/2 x, if I do 1 divided by the a value, 1 divided by 1/2, and I keep change flip, I get a horizontal stretch of 2. So basically we flip that fraction. If I have a number bigger than 1, it actually compresses. If I have a number smaller than 1, it actually stretches.